Just as in two dimensions, when we have a one variable function, f of y equals f of x, a local max means that its value, the function value, is greater than all the values around it, function values around it. And a local min is one where the values are less than the ones around it, less than or equal to. Same is to be said for two variable functions. We call them z equals f of x, y's usually. Yeah, you have a local max or relative max at, all right, and so when we had one variable system, one variable functions, we called them C values, the critical numbers. I guess why we chose C there, why they choose C, but when we're doing two variables system, why do I keep calling them systems? Two variable functions, you need both an x and a y value, and so they usually call it the point A, B. There's a local max at that A, B if f of A, B is greater than or equal to f of x, y for all x, y's in region around AB. So it's, like I said, very same thing. We're just looking, so if we've got this particular function, it may have lumps in it, or like a, just thinking of a kind of a sheet here, and then you've got this kind of mound or whatever you want to call it there. But for that particular AB value, whatever it is, it's bigger than all the points around it. Makes sense, okay? So if you've got, this region around AB, AB is just a XY in the XY plane, if you will. All the other points around it, if you plug those in, their function values are less than the ones at FAB. Makes sense, all right? And then the local min goes the other way. If f of AB less than or equal to f of xy for region around AB. Okay? All right, so makes hopefully pretty good sense there. Now that's not to say there's not other function values greater than that, it's just in a region around it. So we're talking about a region around it. There may be another max out here, relative maximum out here, that's got a larger z value, higher point, but in that general vicinity. That's what we're talking about. All right, now, like we said, how do we locate these? Well, just like we did for the y equals f of x, we look for those critical numbers, c, which were, what were those? How do we get a critical number? Derivative equals 0, or derivative does not exist, right? That's what we looked at. Well, for the two variable, same thing. We'll call them critical points, since we'll have to have an x and a y value. Or they also call them stationary points. Some places may refer to them as that. So critical points of f of xy are a comma b, such that one, okay, so critical numbers, that's f prime equals 0 or f prime does not exist. Well, the thing about that is, now, when we talk about this, we have two partial derivatives to consider. So we'll have to do the partial of f with respect to x of ab equals 0, and that partial of y at ab equals 0. So we gotta have both of them equal to 0. That's, you just have to find two partial derivatives and set those equal to 0. That's basically more or less it. And another way to kind of review what we've been talking about, another way you could say this is our gradient of f at ab equals 0. The gradient of f is the partials kind of put together there. All right. But in general practice, this is how we find them. So that's generally how we list it out. And then, of course, you've also got the does not exist. Either partial derivative does not exist. So that'll be the two possible ways. So it goes hand in hand again with the one variable scenario there. And there's a theorem that goes along with the critical numbers too, and that says if z equals f of xy has a local max or a min at AB, then f partial f with respect to x at AB equals 0 and partial y at AB equals 0. So if it has a local max or min at AB, then those two do equal 0. And an example here, just to kind of show you how it kind of works. All right, say we've got f of xy equals x squared plus y squared minus 2x minus 6y plus 14. If you look at your partial of f with respect to x, you got 2x minus 2. And your partial of y is 2y minus 6. All right, well, if we set those equal to 0, here you would get, what, x is 1. And set that equal to 0, you've got, 2y. 2y minus 6. I think I said y. 2y minus 6, so that would be 3. Y equals 3. And so these two kind of in combination, that's our f of x equals 0, f of y equals 0. So this would be our A, this would be our B. That would make number 1, or satisfy number 1 there. So AB would be 1, 3. Would be our critical point from that. Right? That's our A comma B critical point. There's not any, and then number 2, we don't have any critical points off of that because the partials, we don't have anywhere where those do not exist. Okay? All right, well, in this particular case, we're not going to prove it, but kind of show it in this particular case. What you get, if you graph this thing, well, let's do this first. Let me transform this equation here. Let complete the square on the x's and then on the y's. Here's the x minus 1 squared, and then dy minus 3 squared. So if I do that, I wind up adding 1 and 14, and then so it's got to subtract. That's plus 5. Is that right? Plus 4. Oh, minus 10. That's right. Now just do that because to complete this square, I have to add 1. I have to add 9. So anyway, you don't even have to worry about that. That's not how we're going to do this. What that shows me here is, yeah, if I plug in the 1 for x and then the 3 for y, that's going to give me 0 for those particular values, right? And so the value there would be 4, the z value would be 4. Now, if you think about then other points, this has to be greater than or equal to 0, this right here. This has to be greater than or equal to 0 because it's squared, you know what I'm saying? And so that shows me right there that this 1, 3 critical point, that's going to be a minimum, isn't it? Because anything else, I'm going to get 0 off of those. Anything else is going to be greater than 0 for both of those. And so you're going to get a larger z value. So, you know, kind of working our way through that logically, that's not how we're going to do these, but you do see that we do get a minimum here. And again, if you look at the graph, which I'm not going to, I just got it figured out here. If you go out to x is 1, y is 3, and then z is 4, be up here. Yeah, what you'll, that's our kind of our low point, and the rest of them, you get this paraboloid looking thing here. And so it just keeps on going up like that. But yeah, there's our 1, 3, 4 point. It's the minimum. Okay, so just to show you there that this does typically, this little process right here gives you those, in this case, your absolute minimum, but or local minimums. There's only one for this one. But anyway, okay. Now, that being said, critical points don't guarantee you get a min or a max. That's not what that theorem right there says. Just like this right here, these values, these C values don't give you necessarily a maximum or minimum. Neither do these critical points. And let me just show you one of these, for example. Something we haven't encountered yet, really, because this is a three-dimensional deal, but all right, so note if f of x, a, b equals 0, and partial with respect to y, a, b equals 0, that doesn't guarantee you have a local maximum. All right. Here's what can. Say, for example, we take f of xy equals y squared minus x squared. What are my critical points there? Critical point. Well, to get the critical point, do the partial of f with respect to x, which is negative 2x equals 0. So that would be x is 0. Do the partial of y, which would be positive 2y, set that equal to 0, and so that gives you y equals 0. And so my critical point is 0, 0. Spectacular about it, but that's a critical point. Well, turns out on this one, here is what the graph looks like. See if I can draw it. let's come out here a little bit along the y-axis. Yeah, if you get, we're not going to go through how this one graphs out, but I'm just going to show you here. Let's make it not that tall. What happens here is, yeah, you get this kind of this cross section here is this is a parabola, and the same thing here at 0, 0. But what it does, it kind of swoops down, and 0, 0 at the 0, 0 point, which is 0, 0, 0. It kind of comes down, and then it kind of goes out the same sort of way. And so on this side, you also get a cross-sectional parabola. If you connect some things here, maybe we can get a visual on that. So yeah, you kind of, looks like a saddle. You got a saddle-looking shape, where each cross-section is a parabola. If you cut in the XZ there, but anyway, what we're focusing on is this critical point 0, 0, which is 0, 0, 0, right? That would be the actual point here. Notice though, it is not a minimum and it's not a maximum, because for one thing, well, you look at it here, you say, well, oh, it looks like it's a minimum, but it's all points around it. So if you look at kind of this cross section here, which would kind of do that, you see, if you look at it from that perspective, it looks like a maximum. See that? So it's a minimum this way, but it's a maximum going this way. So, which is it? Well, it's neither one, okay? You can't be both at the same time. What that's known as, it's a saddle point, which is another reason to show you this. So what you have at this critical point is you have a saddle point, okay? So that can also happen. You can have these local maxes and mins, but you can also have saddle points, okay? And we'll talk about how that how you can tell that happens from the derivative here in a second.